Hello students. We sh- the next topic under cluster analysis, that is types of data in cluster analysis. These are some of the small fundamental topics which are required in order to progress further in our understanding of cluster analysis. Yeah, so coming to the introduction, we study the types of data that often occur in cluster analysis and how to pre-process them for such an analysis. So we have a major topic, maybe I will give it to you in my next presentation, which is about given any type of data in the data set, how they can be converted into a numerical attribute so that we can apply similarity metrics such as Euclidean or Minkowski or Manhattan to find the similarity between the data objects. So before going to that, we need to understand certain small fundamental concepts. The first concept is a data matrix. Now, what do you mean by a data matrix? This represents an uh, it represents n objects such as persons with p variables, also called as measurements or attributes, such as age, height, weight, gender, and so on. And there's something called as dissimilarity matrix, which is also called as object by object structure. Dissimilarity matrix, this stores collection of proximities, that is a collection of similarity that are available for all pairs of n object. The representation, from the representation, you may not be able to understand much. Let me straight away take you to an example. So this is an example for a data matrix, and this is an example for distance matrix. Now, if I consider, coming to data matrix first of all, if I consider this x as height and y as weight, or maybe age and weight, yeah. So x as age and y as weight, and a, b till f are six different persons. So A is first person, B is second person, C is third person, likewise F is a sixth person. So observation of every individual is recorded here. So observation of a person A with the age 9 and weight 49 is the first instance. Observation of person B with age 24 and weight 54 is the second instance. Likewise, you have it. You have six observations here, and that forms a data matrix. Now, what do you mean by distance matrix? The similarity. A similarity can be given or dissimilarity also can be given. So in this case, we are talking about dissimilarity matrix here. So A to A, dissimilarity is 0. A to B, what is the dissimilarity between person A and person B? It is given in the form of a numeric measurement, that is 16. Dissimilarity between A and C is 47. Or you can also consider this as a distance matrix. The distance from A to A is 0, distance from A to B is 16, distance from A to C is 47, and likewise all other values here. So that is what is given in a formal representation here. So the data matrix is also called as a two-mode matrix because on the row you have the objects, and as a columns you have the characteristics or the features, attributes, characteristics. And dissimilarity matrix is called as one-mode matrix because it only has distance values there. Now, given a set of values in the data set, how we can ensure that it is a standardized set of values? Why standardized? Because why standardization is required? Because it is not fair to have some measurement in centimeter and some measurements in feet and some measurements in meter. We need to have all the values either in centimeter or in feet or in meters. So we need to make it standardized. So how when an attribute is given, it can be converted into a standardized set of values. So what I have displayed here is a z-score normalization, which is given by ZIF equal XIF minus MF divided by SF. Now, XIF is a first observation, first attribute value. If I have two attributes A1 and A2, and if I want to standardize the first attribute, that is A1, then X11, X12, X13, like that, row wise, it will take every observation value. MF is nothing but it is the mean of A1. Maybe if I have 10 observations, A1's X1 to X10 mean value. And what do you mean by SF? SF is said to be mean absolute deviation. What could be the deviation? So the first value of the observation minus the mean value. So summing up all of these differences of every individual observation minus um, the mean value divided by total number of observations, you get SF. So that value has to be placed here and you normalize the value here, Z score. Now let us see some of the similarity measures. This is already known to you. Just for the sake of completeness, I would like to cover the first one, and the very famous one or the important one is the Euclidean distance, which is defined as follows: xi1 minus xj1 the whole square plus xi2 minus xj2 the whole square, the square root of all the values. So here this one represents the first dimension difference between the first object and the second object, and this one represents the difference between the first and the second object for the last dimension, for the nth dimension. What do you mean by Manhattan distance? Is given by the difference between the first and the second observation for the first attribute, difference plus the difference between the first and the second observation for the second attribute, likewise till the nth attribute. Minkowski distance is given by, or it's a generalized form of a Euclidean and Manhattan distance. If you replace P as 1 here, then it forms Manhattan distance, right? And if you replace P as 2 here, it forms the Euclidean distance. So it's a generalized form of Euclidean and Manhattan distance. But normally for k-means or k-medoid kind of algorithms, we normally make use of a Euclidean distance. Unless and until it is specified in the question paper that you have to make use of Manhattan distance, please make use of only Euclidean distance. Yeah, that's all. In the next presentation, we shall check out how we can convert an attribute of any type into numerical attribute, so that similarity measures can be applied in order to find the clusters. Thank you very much.